what to do, shall we say, when your sample space is some portion of the real line, right? So, all our discrete ideas will have to be changed, right? We cannot do the usual discrete stuff. We have to do, in other words, I mean, well and truly you have an uncountable infinity, right? So, any interval of the real line has an uncountable infinity of points, right? Any interval, A, B, closed or open, does not matter. So, we have to come up with a theory of, start with the theory of sets on the real line. So, you can think of it as set theory has to, so far applied only to discrete spaces, it meets the real line now. So, what does it do? So, you can think, write this. So, so you have to be aware, right, prepared for thinking about unions and intersections of what? Of points taken from the real line. That is not enough, right? You need to also look at intervals of the real line. So, what is, first of all, the first question we need to answer is what is a script f, right? The field, right, identify as, right, a suitable, remember we talked about this Borel sigma field, sorry, we call it a sigma field, right? Go back to your first or second lecture. And also he gave examples of omega being less than, being a portion of the real line, right? Spinning pointer is the most commonly encountered, one of the simplest things to look at. And also you can think of, as I said in the first lecture, you can think of darts or either 2D or 1D, right, whatever. And we assume that we can measure the point to infinite precision, essentially, right? Whatever outcome we get, if we want it to be well and truly a real number, measured to infinite precision. So, there is no, right, we do not want to force this to be a countable set of points only. We want it to be as free as it can possibly be. Right? So, that is the omega. So, what is the suitable sigma field for such cases? The answer is you cannot use, first thing is what can power set of such a omega is too big, right? Again, this is a deep result in maths and I am not going to give any justification for this. The power set of such an omega, whether it is any if it is for any subinterval of R, of course for R it is whatever, right? Any interval of R, if you try to look at all possible subsets of that, they say that the maths books say clearly that it is too big and it cannot be used because we cannot give a probability, assign probabilities to all of these subsets in a consistent way. That is what they say, and that is again, the no book that I have looked at ever gives a nice explanation of why it is too big. So, we will have to just leave it at that, right. Hopefully some of you might take some analysis courses in mass real analysis or measure theory or some such thing. If you do that, you will encounter this statement again, and there you may encounter some, right, some more details about this. So, what everybody does is scale down from a power set, that is set of all possible subsets of such an omega, to what is called the Borel field, right. We use the so called Borel field. Borel is the name of a mathematician, by the way, right. The Borel field generated by intervals. Now, to to flesh out what I mean by generated by intervals, by this term generated by intervals. Supposing you start with, right, assuming let omega equal to R itself, right. After all, right, any subset of R you can easily, any portion of R you can easily generate, you can do the same thing, it's not a problem, right. So for simplicity, let assume that you have the entire real line, you have to, right, you have to generate this do this action of generating this Borel field. What you do is start with some open interval a b, where a is less than b and both are real numbers, any a b, and then you take unions, intersections and so on of such a b. So if you start with a b, how do I get the closed interval right? Let me write a couple of things here. Then this is an interval which does not include b, but neither includes a nor b, but if I want to include I didn't mean okay, let me write it that doesn't follow from this. If I want to generate an open interval from a closed interval, right, I can do things like this. There's no then here, I will erase the then. I have this countable union of that is, if I take these closed intervals for different values of n, if I take the union of all of these, see, this is what I mean by saying set theory meets a real line, right. This is maybe new to some of you, this kind of manipulation, but this is what we see in books, right. This kind of union gives you can go, it links this a sequence of closed intervals. Each of this is a nested closed interval. You can see that as you make n bigger and bigger, you are actually making the interval slightly larger and larger and larger, right. And ultimately in the limit, as n goes to n is an integer, right, positive integer, you get the open interval AB. So this is basically what the real analysis books talk about as the connection between open and closed, right. How do you, so in a way that is to get open from closed. How do you get closed from open? Closed from open is very simply got by the union of this AB, union of what? A and union B. These are singleton point, just this points, just the one point AB. So this is the closed interval, right, on both ends. So I am just giving you these examples to show how you can manipulate these intervals. Of course, this is right. We are not just going to do this. We are going to take the complement of AB. We are going to take the right unions of disjoint intervals, and so on and so forth. Right. So basically, if you do this, in other words, let me see write it in English and then also write. You repeatedly form new sets by taking countable unions and intersections and complements, right. We form thing is, we are allowed to take countable unions like this. In fact, there is something else you can do with the okay. Where does a countable intersection arise? A countable intersection, I can also write one more thing here. It's not something similar to these two, but not exactly related. The singleton point A, for example, is the countable intersection of what? Supposing I want to write the singleton point A as a countable intersection of some, that is, I want to take an interval and shrink it to a single point. What should I do? I have to take the interval a minus 1 by n comma a plus 1 by n, this open interval, and if I do this n equal to 1 to infinity, this it shrinks to this one point. Note that this a is inside this interval for all n. So this is an example of a countable intersection, right, and of course complements. So if you of all intervals, open, closed, doesn't matter, right. I have already shown you how open and closed are obtainable by simple countable unions. So if you do all this, you get what people call as the Borel field. So the key idea is intervals, which is the jump now from the single points, the isolated right individual points that we had earlier. So this is called the Borel field of the real line. And notice this has nothing to do with probability at all. This is a far more general concept, right, which is used in a bunch of different construction arguments involving the real line, and has nothing to do, not specific probability. Probability happens to ride on top of this Borel field, that's all, right. So what does the Borel field contain then? If you look at it, it contains all open intervals. Let me, I should list them out clearly one more time. Okay, before listing them out, let me also point out that no interval can be formed as a countable union of the points inside it, right. You can say, is AB of this kind, is this a countable union of all the points inside AB? No, because the number of the points is in any interval AB is uncountable. So you cannot express this interval AB as a countable union of this kind of the points inside the interval. So that is, in other words, this union of over I of AI or Xi cannot form an interval. Let us say I equal to infinity, does not matter, right. No countable collection of points can be combined to form an interval. This is one more very important fact relating to the real line. So this much background of real analysis we need, right, we cannot do without, but the good news is that we are not going to go back to this anymore, right. We're just setting the stage, and then once we realize that it's intervals we need to focus on, we grab that and say, aha, we know how to deal with intervals, so we're sort of done. In a way that is true. So the focus shifts from points, discrete points, to intervals. Is that okay? All right. So what does the Borel field then contain? It contains all points. It can, so we will use this F. Let me call this F the Borel field, right? What does it contain? All open intervals A, B. Now why should I separate out these open intervals and closed intervals? Because when you look at infinity, it occurs only as an open interval. So this includes minus infinity B, including minus infinity B and A comma infinity. So typically infinity occurs only as an open interval, not as a closed interval, because right, it's a concept in some sense in such intervals. You are just saying the set of all real numbers smaller than B here. Just to write that, you are writing infinity as a kind of a placeholder, minus infinity is a placeholder. Similarly, the set of all real numbers bigger than A is this. So typically you do not include, say, okay, the real line ends at infinity, that right, it's not that, usually that's not the way in which it is understood. So the closed intervals are all closed intervals of course for finite AB. And of course the half open, half closed, I don't want to get. It also includes all points, all individual real numbers, right? Why? Because how did I get this? By taking a countable intersection, right? So all real numbers individually are included in F, not just the intervals, points are also included. That is, and all unions of the above sets, right? So, so this is, I'm not claiming that this is completely exhaustive. I think it's mostly anything that we want to, any interval that we want, or a union of intervals, I think should fall into one of these categories, right? If you have, for example, AB union CD, that will be perfectly valid. Right, a union of two disjoint or even overlapping intervals, it does not matter, right. So this, since the integers for example are a special case, right, of real numbers, this countable union of the integers, like the set of all integers, is included, but that is not the only thing. You can have a countable union of irrational numbers, for example, things of that sort, they are also included. So it is in fact very hard to locate a set which is not in this collection, a subset of the real line which is not, it is actually not easy to construct a subset of the real line, right, which is not in this collection. But apparently such subsets do exist, which is what we alluded to earlier, and that, right, the power set of the real line would obviously include those also, but those are not trivial at all to construct, right. But as I said, this is not a mathematics class, so we cannot stray too far from our path, which is to start, look at applied probability and not these fundamental questions of what is consistent with the countable union, what is not consistent, and so on, right. As long as, right, we can work with this, we will, right, and we are going to stick to this, and all the things that we do, we will keep going around here. So all discrete probability with integers, for example, is included here, right. That is what I want to say. So this includes all the sets of integers that we have seen so far.